In the second part of this tutorial, I'm going to show you how to write the output of the molecular dynamics code we wrote in the first part and how to visualize this output in OVITO. Going back to the code that we wrote in the first part of the tutorial, there were three variables: the radius, frequency, and the output file name that we did not use in the first part. And we're going to need all three for writing the output and visualizing the data. You'll notice that in this version of the code, I've included a few comments and also a description of the different functions and the doc strings. And you can download this version of the source code from the link that will provide in the video description below. The first thing I'm going to do is modify the main solver function run by simply extracting the radius, frequency, and the output file name from the arguments dictionary that's being supplied to this function. We can now use the radius to create a NumPy array, which I'm going to call radius as well. So I'm overriding the variable radius with a NumPy array of size n atoms, and it's going to contain just ones and multiply it by the radius float. Now, in order to account for polydispersity, we can change this vector into whatever is the ratio size for atoms having different sizes, as you would for the masses as well. And the next step is to write the output every frequency number of steps. So we're going to use the modulus operator, the percentage, and whenever this is 0, we know that the step is a multiple of frequency. We're going to call a function that we haven't defined yet called write output, and it's going to take the output file name, the number of atoms, the step, simulation box size, in addition to other arguments that could be the atomic masses, radius, positions, velocities, or forces. These are going to be NumPy arrays. Now I'm going to define this function in a separate module called dump, and that means we have to import this module, import.dump, and I'm calling this dump because this module will contain the only function, write output, that will write the NumPy arrays to a dump file. Dump files are used by LAMMPS, the molecular dynamics solver. They're quite easy to read. The first thing to do in the dump module is to import NumPy as MP, and then define the write output function. And then we're going to pass the output file name, the number of atoms, the time step, the simulation box size, which is a tuple, and then finally the NumPy arrays that represent the atomic attributes that we're interested in writing as an output. These could vary. The user might be interested just in writing the mass or the forces or a combination of the positions and the velocities. So it varies, and one way to handle this is by just passing these as optional arguments in the form of a Python dictionary, which we're going to call data. And then using the with statement with open output file name, and the mode I'm going to set to append with A, because I don't want to overwrite the output if it exists, if this file already exists. But if you're not interested in this type of behavior, you can use W just to overwrite the file if it exists, or you can create another input variable and let the user control this. Here I'm just going to set this to append, and I'm going to write the time step. So I'm just gonna copy paste this, \n in order to break line, again break line, and include the time step. So we've written the time step with this. And the next thing is to write the number of atoms, and again break line with a \n and then fp.write breakline dot format. It's going to contain a number of atoms. Now, the next thing we need to write is the simulation box size. This would include the boundaries, the minimum x, maximum x, and similarly in the other two directions. Now, LAMP's dump file format always defines the simulation box size in 3D, and the boundary conditions are specified here. FFF means that they're fixed. Usually they're PPP, periodic. It's not going to matter for all purposes for visualization, but if you're doing quantitative analysis, depending on the software you're using, it might be important. For now, we're just going to keep this hard-coded as FFF. Now, the next thing we want to do is actually write the simulation box boundaries. I have to break line here. And in order to do that, I'm going just to create a simple for loop over the box, which is a tuple, two-dimensional tuple. So let's call this dummy variable box bounds and loop over box. And then we're going to write the minimum, the maximum, break line, dot format. We're going to just pass this as a tuple. It's going to be of size 2. So box bounds, minimum and maximum will go in here. And this should complete writing all the necessary, or rather the mandatory variables for a dump file. The next thing would be the optional atomic attributes. So if data is empty, there would be nothing to write. And if it contains actual data, we're going to actually write this to the dump file. Now, before we do that, we have to break any two-dimensional array into one-dimensional arrays, because in the dump file, you'll notice that velocities are broken into x, y, and z components. Positions x, y, and z. They could be in any order, but they must be one-dimensional. Now, the positions and the velocities, just for convenience, we define them as two-dimensional arrays. So we have to break them here into one-dimensional arrays. We have to do a simple transformation. And one way to do it is by, first let's create a keys variable, which we can directly extract from the keys function in data. And then let's loop over keys. Now, if data is empty, then there's nothing to loop over. Otherwise, we're going to extract the data key NumPy array, and if this is two-dimensional, then we have to make a simple transformation. So let's create here a Boolean variable called isMatrix, and we're going to extract the length of the shape of data key. Now, the shape function returns a tuple. If it's of size 1, then you know this is a one-dimensional array. If it's of size 2, then it's going to be two-dimensional array. So the len function returns the length of the size of this NumPy array, and if it's greater than 1, then isMatrix is going to be true. So if isMatrix we're going to do a simple mapping, select all the rows, column I in data key, and then we're going to map this to its x, y, or z constituent. So for that purpose, we need the key, and we need a new variable called axis, and we're going to select the ith component of the axis tuple. So axis is something we haven't created yet. let's create it over here. Axis equals, it's a tuple of size 3. Simulation cannot be more than 3 dimensions, so we just include the x, y, and z strings in the axis tuple, and then we're going to extract the number of columns in this matrix, so two-dimensional array. We can just do it through data key.shape. The first entry in this tuple is going to be number of rows, which I've just assigned the underscore to because I'm not interested in number of rows. And the second entry is going to be number of columns. And now I is going to be this dummy variable that goes from 0 to number of columns minus 1. And then we're creating in data a new entry. This is the new key that's going to be, let's suppose key is v, standing for velocity. Then this is going to be v underscore x, and then v underscore y, and then v underscore z. And it's going to contain all the entries in the 0th, 1st, or 2nd column in this two-dimensional array. Now, if, however, key is position, then we don't want to create this as x underscore x. If you look at the dump file, the positions are just x, y, z. The velocities or the forces would be v underscore x, f underscore x. If it's an angular velocity, omega underscore x, and so forth. So for this purpose, we have to make sure that key isn't equal to position. If it is, then we're going to make a slight modification to this code. We're just going to call this x as I, so it would be x, y, or z that we're mapping. And this should do it. The last thing we're going to do, if this is a matrix, is delete the data key, simply because we've mapped each column in this two-dimensional array to its x, y, and z components, so we don't need it anymore. And then we're going to update the keys once this for loop is done. If there are no two-dimensional arrays, meaning that the user is just saving the mass or the radius, then this for loop will not be executed and the keys will just remain intact. Otherwise, the keys must be updated. Now we could write the atomic attributes. Let's go back to the dump file, and you notice that this starts with item, atoms. So we're gonna include this here, and then add to this the different keys that we have, the velocities, positions, and so forth. We don't know these right now. It depends on what the user is going to supply. So we just multiply this placeholder in the string by the length of the keys. And then for the format function, we're going to include keys as a tuple. And this should create the 9th line in the dump file for all the different atomic attributes that have been supplied by the user. If there's nothing, then it would be just empty, no attributes. So the last step now will include writing the output. So I'm just going to create an empty list called output. Now before proceeding, I noticed that I have a typo here. It should be I in range and columns. And there's one thing that I forgot also here is to just to break line. So the last step will involve looping over all the keys and using NumPy's horizontal stack, hstack, to append the data key to output. So we end up with a single array, one-dimensional array of size n atoms by whatever is the length of the different arrays stored in data. So if we're just saving the positions, this array would be of size n atoms by 3 for a three-dimensional simulation. So if the length of output is not 0, we know that output contains certain data to be saved. We're going to use NumPy's saveText function and save this to the file, the output file that we've already written the different attributes to, and then we're going to use the output, which is now a NumPy array, output's reshape function. Now reshape will enable us to transform this one-dimensional array into a two-dimensional array, so we could save it as a matrix or as a table of size n atoms by whatever is the total number of attributes that we're writing. So in this case, we're going to reshape this into n atoms, comma, and length of data. And it's important to include the keyword F for Fortran, because by default this is C. When reshaping a NumPy array, we want to make sure here that it's done column-wise. So the order equals F signifies that we want to store these arrays column-wise, which is the default way of basically allocating memory in Fortran. In C it's row-wise, so the keyword C would just give us completely the opposite. It's the transpose of what we're looking for. So we want to make sure that the order here is F, and this should complete this function. Last step before we run the code is to go back to Langevin.py and complete the arguments for the right output function. So we're going to write the radius, the positions, and the velocities. It's important to pass the velocities as the variable v. The keyword v here is very important. Same thing with positions, because otherwise the right output function wouldn't know that we're writing here the atomic coordinates. We can also pass forces for f, and this will be written as f underscore x, y, and z in the dump file. So if we try to run this for 100 atoms and call the trajectory output file traj-hydrogen.dump, if we run this in Python 3, we're going to get an error in the dump module, line 21. And this is simply because in Python 3, whenever we call the function keys on a Python dictionary, this returns an iterator rather than a list. So if you run the same code in Python 2, it's going to work just fine. But in Python 3, this is going to be an iterator, and since we're modifying the Python dictionary in this for loop, it's going to vary, and the behavior doesn't make any sense, which is why the interpreter complains. We don't want the Python dictionary to evolve while the keys are changing. We want the keys to be constant, and therefore we would encapsulate this as a list. So we're converting the iterator to a list, make sure the keys is a constant, and now we can modify the dictionary data. And this should make the source code work in Python 2 and Python 3. So we go back to Langevin.py and run this again. And now it works. The temperature is fluctuating a lot more than before because we just have 100 atoms, but it's around 300. Let's try to open the trajectory file and see what it looks like. So it's being written every 100 steps as expected. We've got the radius, we've got the velocities, and we've got the positions as well. If we try to run this in 2 dimensions, we're going to have to make one slight modification, starting with the temperature here. In the first part of the tutorial, I've assumed that there are 3 n atoms degrees of freedom, but that's for 3 dimensions. This should be n dimension, so I believe we've defined, we've called this just dimension. So for 3 dimensions it would be 3 indeed, but for 2 dimensions it should be 2, and for 1 dimension it should be just 1. And the other modification is, because of the dump file format always expects a 3-dimensional simulation box, it's important to make a slight modification here. In case this is a 2D or 1D simulation, we're going to make a simple for loop. Take the length of the box, and then we're going to subtract this from the length of the axis, which I'm going to change its place of modification right over here. So if this is a 3-dimensional simulation, the for loop is not executed. There's no point, because this is going to be 0 for I in range 0. We'll return absolutely nothing. There's no for loop. But if that's not the case, well, I just realized it should be the opposite actually. Length of the axis minus length of the box. So the length of the box is 2. This is a 2-dimensional simulation. Then we would have to execute for I equals 0 only once and write, well, we could just write actually 0, 0, because we don't care about the z dimension in this case. So this would be a 2-dimensional simulation box along the x and y directions. And similarly, if this is a 1-dimensional simulation, we would end up with 0, 0 on 2 separate lines for the y and z axes. So let's save this and go back and run this simulation. And you notice we still get here temperature the same as before. Let's try to reduce the dimensions in the simulation to 2 and call this hydrogen-2D. And then we run it again, and the temperature is again close to 300. Fluctuations have increased a little bit, which makes sense. There are fewer degrees of freedom in the system. So the last thing I'm going to show you is how to visualize this. So for this purpose, I'm going to be using OVITO, which is an open source visualization tool. It supports the dump file format. It's used a lot in molecular dynamics simulations or coarse-grained molecular dynamics simulations. So I have here OVITO open. It's pretty easy to set up, and I'm gonna first load a 3-dimensional simulation. These are the 100 atoms that we simulated, and you can see that the reflective boundary conditions, the first part of the tutorial, are enforced. The atoms can never escape the simulation box. Now let's take a look at the 2-dimensional simulation. And you notice here that the simulation box size is indeed in 2 dimensions, and the particles are just fluctuating.